Good afternoon. So this is the final lecture of the series. So we are going to talk about engine performance, rather automotive performance. So by the end of the lecture, you will be able to define the metrics used to measure engine performance and how they are being used, and also describe how the metrics vary with different engine parameters. So the engine performance metrics are generally the torque, power, mean effective pressure, volumetric efficiency, specific fuel consumption, and fuel conversion efficiency. So these are just the terms that we use. We will discuss what all these terms mean. So there could be torque, power, mean effective pressure, volumetric efficiency, mechanical efficiency, specific fuel consumption, and fuel conversion efficiency. So volumetric efficiency actually we discussed in our second lecture. You might remember, but the rest we can learn today. So torque and power are interrelated. So torque, power is actually the rate of torque, if you want to put it that way. So engine torque is usually measured with a dynamometer, and the engine shaft is connected to a rod like this. That's your engine. That's the rod. So you need then what you find here is now if you apply a torque here, that torque or the load here, that load can be counterbalanced by a load using an extended shaft. So the rotor is electromagnetically hydraulically connected to mechanical friction or by a stator. So this could be mechanical friction. This load could be mechanical friction, electromagnetic force, or hydraulic force. So this is called the stator. This is called the rotor. So the force exerted on the stator with the rotor turning is balanced by this by the load set. Okay. So if you write an equation for this for the torque and the load. So torque exerted by the engine is basically that force times B. So that's the torque. So if you were to have a brake at the stator, basically your B will be higher, so your torque will be so your force will be B will be smaller, your force will be higher, but you will have the same torque. So torque is T is torque, F is the force, and B is the lever arm length. And the brake power. Now this you are using a brake here, so the brake power is that 2 pi nt is your brake power. So your torque times how many times you how many times you rotate the engine gives you the power. Brake power is in watts. N here is the crankshaft rotational speed. So torque is the T given by T. So 2 pi is the perimeter. So yes. So because in one revolution, so it rotates 2 pi. So there are a couple of links here for you to look at how dynamometers work. So I will leave you to click the link later and go and have a look. Power and torque are normally expressed in more user-friendly units like kilowatts, or torque is expressed in Newton meters, or in the older units like non-metric or imperial units, power is given in horsepower, and torque is given in lap foot or pound foot. Okay. So therefore, your PB is the brake power in kilowatts, would be 2 pi nt over 1000. Okay, so in kilowatts it's 2 pi nt over 1000. So this is the conversion unit for pound feet, but we are not. It's just for the sake of completion, but we are using standard units in kilowatts. Okay, so 1 kilowatt is about 1.3 horsepower, and 1 horsepower would be like 0.75 kilowatt. But yeah, so that is just to look at. That is just to see. So now, for example, cars, etc., they still use this horsepower thing. So 100 horsepower kind of, or the PS unit that is used in Germany, etc. So they are quite equal to a horsepower. So, but these conversion units are just for sake of completion. Okay. So I want you to do an exercise. Draw a PV diagram for Unreal Autocycle engine, as you remember. Please take some time. Post this video and do that. Yes. So that would be your PV diagram for the real auto engine. So suction, compression, heat addition, power, and exhaust. Heat release and exhaust. Yeah. So if you want to get the work done in this, so this is basically a PV diagram. Yes. So this is a PV diagram. So that is positive work. That is actually negative work, right? So if you can get the volume, get the area of this PV diagram, you will get the work done. So that's the positive work done. Is given by the red area, and the negative work done, that is the work that done on running the engine, would be given by the negative area. The blue area. Okay, red area positive work, blue area negative work. So the net indicated work per cycle is the actual work that is given by the engine. Okay, so you have to deduct the blue area from the red area to get the actual work done, the net work done. Okay. So PDV, so that would be the PDV would be the integral of P pressure in the volume diagram, PV diagram. So this is called the gross integrated work per cycle. Is the work delivered to piston or expansion and compression. So that's the gross. That gives you the red area gives you the gross indicated power, and the net indicate. So the pumping work. So one between 1 and 5 you have the pumping work. So that is the so gross indicated work minus the pumping work is actually the net work. Okay. And then so power per cylinder is given by work done by the total whole engine divided by the or the so or divided by the number of cylinders. So this is for example, if this is your dyno, that's your dyno. So that's your engine. If that is your engine and if it has 4 cylinders, so in here your n would be 4. Okay. So n capital N is the number of revolutions per second. Okay. In here n is the nr is the number of revolutions per stroke. So for 2-stroke, 2 for 4-stroke, and 1 for 2-stroke. Okay. So power and work basically they depend on the engine geometry. The mean effective pressure allows comparison of the work done between engines independent of the cylinder volume. So what you do is you get the mean effective pressure for the engine, not per cylinder. Okay. So MEP, mean effective pressure, is the work per cycle divided by swept volume per cycle. So basically, so you divide, now you get one work per cycle, and you divide that by swept volume. So that then you will get the mean effective pressure. So WC is the works per cycle, and VD is the swept volume per cycle. So what you do here is you have you get these areas, that area the red area minus the blue area. If you equate that to a square box of the same volume times a pressure, now that pressure will be the mean effective pressure. Okay. So P would be Wn over Nr. So that mean effective pressure is given by W over VD or PNR over VD. Okay. So mean effective pressure is in kilowatts. Power is in kilowatts perhaps normally, and VD is given in decimeters liters. So MEP can be given in kilopascals like this. Okay. So given that your displacement is 1994 and your brake power is 2009 and your torque is 307 Newton meters, that is in kilowatts, so then you can calculate the speed and the BMEP and so on. So just use PB equals 2 pi nt equation. Okay. Now pause the video and do the calculation and then look at the answers. Okay. So your answers should be speed, it should be 6,500 for the first engine, and BMEP should be 1935, and for the second engine your speed should be for the second engine your brake power should be 55 and your torque should be 250. So mean effective pressure is defined by the location and method of calculation. So brake mean, there is a brake mean effective pressure relates to the brake torque. So the brake torque means once you apply the brake. So gross indicated mean effective pressure tells you the mean effective pressure without friction. Okay. So basically, brake power plus the brake power is actually gross indicated power minus the losses. Okay. So net indicated mean effective pressure, it relates to the in-cylinder power over the complete engine cycle. Okay. So pumping mean effective pressure relates to the work from moving gas in and out of the cylinder. Okay. So note that pumping mean effective pressure is equal to IMEP minus IMEP gross minus IMEP net. Okay. So friction mean effective pressure relates to theoretical effective pressure to overcome friction. Okay. So FMEP is equal to IMEP N minus BMEP. Okay. So mechanical efficiency is the ratio of the useful power to the indicated power. So BMEP over IMEP is your mechanical efficiency. Okay. And then mechanical efficiency is usually the range, it's usually in the range of between 75 to 90 depending on throttle position. Okay. And then you define what you call specific fuel consumption. Specific fuel consumption is the indication of how efficiently the engine is using the fuel supply to produce work, and it's defined as the fuel mass flow rate per unit volume. Okay. So specific fuel, unit per unit power. Specific fuel consumption is given as the fuel flow rate divided by divided by power. So m dot f is the mass flow rate, p is the power. Okay. In watts. Okay. Um, so again, so you need to be careful of the units, but if you use you initially you use SI units, and then you can give it in whatever units you want. Okay. So a specific fuel consumption has units. A dimensionless parameter is more convenient. So the fuel conversion efficiency is work produced per cycle divided by fuel energy supplied per cycle. So that would be the fuel energy supplied per cycle is equal to the mass of fuel times the heating value of the fuel. So that would, if you write that one, WC work per cycle divided by MF Q HV. If you divide multiply MF time Q HV, you will get the heating that you have supplied. Okay. So here HV, so heating value, you need to get the lower heating value, lower calorific value, LHV actually. Okay. So that would be usually N should be equal to 1 over specific fuel consumption over QHV. Okay. Then you have what you call the volumetric efficiency. Volumetric efficiency, you know what it is: 2 pi m 2 m dot a divided by rho VDN for 4-stroke. Okay. We have done that before, so I'm going to go through this very quickly. So for naturally aspirated engines, we know that its volumetric efficiency would be about, between 80 and 90%, and for turbocharged engines, it can be greater than 100%. Okay. So we will look at how the engine parameters vary with speed. So usually, when the speed increases, your torque normally increases, your power definitely increases, but at the same time, your brake power, etc., and the friction power also increase. Therefore, you have a maximum torque line at a certain speed, and then the efficiencies, etc., will go down, and your losses will go up. Therefore, it will come down. So you will get the maximum torque at a certain point. So of the RPM. So beyond some RPM. So if you put your foot down, if you sit on the throttle, it won't give you the maximum torque all the time. Okay. So engine, you can draw a graph of BMEP versus engine of its engine and piston speed. So these graphs will give you the increase of brake specific fuel consumption. This is constrained by actually the volumetric efficiency. Okay. So brake specific fuel consumption can be increased. It is increased as emitted and need more fuel power. Okay. So you can say that this can friction mean effective pressure when it increases. Friction mean effective pressure increases with speed. It decreases with speed as well. So this is just a engine performance map, but the performance parameters would be power is equal to Wn. W is the work. N times NR is the number of revolutions, whether it's 2-stroke or 4-stroke. And if you substitute thermal conversion efficiency, so your thermal conversion efficiency would be work divided by MF QHV. Okay, so power would be the thermal conversion efficiency times mass flow rate QHV N over number of revolutions per cycle. So you can get the air fuel ratios as well, MF over MA, in these terms, and also substituting volumetric. You can substitute volumetric efficiency as well. So you can write equations for the power. Specific power is power divided by piston area, and so mean piston speed, if you can substitute the mean piston speed to the equation as well. So you can if you take this equation, so completely this increases this efficiency, the work consumption efficiency increases with power over specific power, and increased in the volumetric efficiency. If you have higher volumetric efficiency, your power will be increased. So if your air density is higher, your power will be increased, and your your mean piston speed is higher, your power will be increased. And fuel to air ratio, if you increase that one within reason, that again it will give you more power, and increased fuel heating value will also give you power. So this equation is quite important to determine how much power you can gain. Okay. So I guess this is a fairly short lecture. Hope you have learned the engine measurement parameters, like performance parameters to discuss, and then you know how these metrics work now. So that finishes our formal lectures. I will see you on Thursday lecture and Wednesday tutorial class. Then we will go through any questions that you may have, and we can have a revision session somewhere in January. I'll arrange that one and let you know the date. Okay. Good luck with your studies, and thank you for listening to my lectures. Thank you.